Hi, I'm Rolf Clackdoyle, and my postdoc, Feriel Khellaf, who worked with us until the end of last year, was responsible for the main theoretical results. Somewhere deep in this talk is going to be a little theorem, and she was the one who came up with that and did the bulk of this work. So it's about trade-offs between redundancy and increased rank, blah, blah, blah. Doesn't have much meaning, but the basic theme here is about region of interest reconstruction. So when we say region of interest reconstruction, we're talking about the case when you have this. So let's stay in 2 dimensions for this talk, although nothing is special to 2 dimensions, just for illustration. So if you have a plane of measurements in 2 dimensions, and there's not enough measurements to reconstruct the whole slice, but there is enough measurements somehow to reconstruct part of that slice, and that's the piece we call the region of interest. So usually all the background behind that's been going on this has been developing for about 20 years now, and always in the analytic reconstruction domain. So it starts off with the integral equation, and there's Hilbert transforms in there and all this kind of stuff. So today it's going to be presented in terms of the usual approach in iterative reconstruction, when we start with a system matrix, and that's defining our problem. And then I'm going to present region of interest reconstruction in terms of matrices and things like that. So it's not analytic for once. Okay, so here's my system matrix. S is the system matrix. Y is going to be the measurements. So in this case, the sinogram arranged as a single long vector. X then is the vector of pixels. So whatever it is formed as a single vector. And you have the usual imaging equation where S is the system matrix. So, and the reconstruction, of course, problem is to find X if you've given the sinogram. So, and you've given the matrix as well. Now, in the case where the matrix has redundant rows, okay, so if the rows depend on each other, then there's a possibility that you might not get a solution. If the rows are all independent of each other, then no matter what Y you start with, you can always find an X that'll solve the system. But if the rows have some redundancy, then Y has to have the same redundancy in order for there to be a solution. Maybe a simple example, if the first row equals the second row, then you definitely want Y1 to equal Y2, otherwise you have no solution. I want to avoid all that discussion. I want to just say we're going to assume for the rest of the talk that there is a solution, that Y really is in the column space of the matrix. It's in the range of the matrix. And I justify that by saying, you know, almost always in tomography, that's not the case. Almost always, in fact, I'm safe to say always, the measurements you make are not consistent with the model. There's some kind of noise that messes it up. But the procedure after that is to say, well, I need to do something. And there's various techniques of doing it. The most common is probably least squares. You do a least squares minimization. What that really means is you take the measurements you've got and you fudge them a little bit. You just change them a small amount so that they are in the column space. And then you go from there, and that's how you find your solution. So all I'm doing here is I'm assuming that that step has already been done. So you've got the raw data. You've now decided what measurement in the true range of the matrix you want to deal with, and then we go from there. Okay. So what I'm doing is I'm avoiding a whole section of stuff which is not relevant to this talk. So I'm going to illustrate things as I go. I think it's always helpful. I'm going to do a tiny little example. So too tiny to be even considered faintly tomographic. The system matrix is going to be 8 by 9, 8 rows, 9 columns. 9 columns means 9 pixels, 9 unknowns. I guess that means the image is 3 by 3, so it's pretty small. And right away, because there's only 8 measurements, you know that you have no hope of getting unique solutions. Our objective here is to be able to get a unique solution to the system. So right now, we've already got the situation where there's no hope to get a unique solution for the vector X, and we cannot get the unique image X that matches the data. So when I talk about ROI pixels, what I'm talking about is those pixels that magically can be reconstructed. Even if the whole image cannot be, then for some, it's possible under special circumstances that some pixels might be reconstructed anyway. Another way to say that is the vector X cannot be solved uniquely, but there might be some components of the vector X which are uniquely solvable. Okay, and those are the ones we call the region of interest pixels. So there's a mathematical definition of that, which basically amounts to saying that you can row reduce the matrix and find those particular elements. But let's not worry about that. The concept here is that you can find these values. So again, I'm doing this 8x9 example, so we're sure that there's no hope to get unique solutions for the whole image. So here's the example. Those blue lines are the measured rays. We're using a simple line length model. So you see 8 blue lines, those are the 8 measurements, they correspond to the 8 rows. The oblique ones have length square root 5 over 2 as you go through the pixel. So you're full of square root 5 over 2 and a bunch of 1s when the lines are horizontal or vertical. So that's my system matrix S for this particular model. And we're going to look at that. So you can actually, by inspection, notice that you can find X1. Okay? So if you want, look at the matrix, and you can solve that. Or it's maybe even easier to look on the right-hand side and look at those arrows. If you look at Y2, it's the sum of the left column. Look at Y7, it's the sum of X4 plus X7. So you basically subtract X7 with some normalization from X2, and you get X1. So you do get the solution X1 for this. And in fact, you also get X2 and X3, despite the fact we have this huge null space. So I guess I said a 3-dimensional null space in there. So I said a minute ago we had a 1-dimensional null space. Well, it turns out for the system, I'll get to this in a minute, there were actually 2 redundant rows. So there's only 6 pieces of independent information in this system. And nevertheless, we can still get 3 pixels out of that. Now, how do those 2 models jive with each other? How can you have a large null space and yet still get something which is unique? And the answer is because in systems, if the null space happens to lie perpendicular to one of the axes of the coordinate axes, then as you travel around the null space, picking off many, many different solutions, you don't affect that direction of that coordinate axis. And that's what's happening here. So it turns out we have a 6-dimensional null space, which happens to be perpendicular to the 3 axes in the X1, X2, X3 direction. So that's how you get a large null space and yet still get uniqueness someplace. Okay, so that's basically the background to remind you how region of interest reconstruction works. And now we're going to move on to some of the new stuff. The important thing is I'm going to talk about rank a lot. So I'm just going to remind you or suggest that the best, for this talk, the best way to think of it is the number of independent rows of the matrix, which is the same essentially as the number of independent measurements you get when you measure the system. So as I said, this particular matrix only has 6 independent rows, therefore 6 independent measurements. With 9 unknowns, you of course have a 3-dimensional null space. Now, if you adjust the matrix somehow in such a way that you manage to increase the rank, okay, so you manage to remove a bit of redundancy and get a new independent piece of information, okay, that obviously immediately reduces the size of the null space. Okay? But it does not necessarily generate any kind of region of interest pixels. Okay? The usual situation is if you increase the rank of a matrix, you just increase the rank, but you don't get anything out of that. Okay? That's the most common situation. What we're going to talk about here is the situation when we can break that. So this is the little theorem that Feriel came up with. This is the situation when you can get new region of interest pixels. So you start with a matrix S. It can be any dimensions. It doesn't have to be long. And it can be M and N can be anything. Either one can be bigger than the other. And we have another matrix C, which is exactly the same as S, except for one element, which is different. And that element is in row A and column B. Okay? So we change one element, and by changing it, we happen to have increased the rank by 1. So we've managed to find a way to increase the rank just by making one little touch up to the matrix. Okay? And this could be true even for huge system matrices. One element might just do the trick. Okay? You change it. And what's the conclusion of this theorem? Well, there are 4 things. Firstly, the pixel corresponding to that row, so pixel XB, can now be uniquely reconstructed. It now becomes an ROI pixel. The second comment is that it was not reconstructible before with the previous matrix S. Okay, so we really have something new. The third thing is all the region of interest pixels that happen to be available from the matrix S are still there, so nothing got lost. And the last thing is that you might even have, if you're lucky, you might get another one for free. So you don't necessarily only get one. You certainly at least get one new pixel, and you might even get more. Okay, so that's the little theorem. And now we're going to play with that just to emphasize. We'll do, oh, sorry, yes, the corollary. If you apply that theorem multiple times, so k times over, then you just say the corresponding thing. So if you take a large system matrix and you change 13 of the values and you get an increase in rank by 13, then you get 13 new pixels and you don't lose any pixels, and you might even get more than 13 if you're lucky. Okay. So let's have an example. Let's see how that works, just to make that a bit more concrete in our minds. So there's my original system matrix S, the same one we had before. Here's C. I've changed one element down the bottom on the bottom row there. So the last measurement line has been changed on this contribution of the 6th pixel. So it's the 6th column. I've just divided it by 2. That was enough to increase the rank of that matrix. So it went from rank 6 to rank 7. And therefore, pixel X6 can now be reconstructed. And it definitely could not have been reconstructed before. When I say reconstructed, I mean uniquely reconstructed. And maybe there's something else that could be reconstructed as well. That's just the statement of the theorem. So let's take a look. So here's what's actually happened. When I changed that element of the matrix, that red line is represented the last row. It's the ray that represents the last row, is represented by the last row of the matrix. And that ray just shifted a little bit to the right. So it's a small change, but by shifting to the right, the contribution of X6 became half of what it was before. If you look at the line length of that red line now going through X6, it's half the length that it was before. So that was the change that was done to the system, expressed in terms of the system rather than the matrix. And sure enough, according to the theorem, you can sit down and virtually by inspection, you can see how to solve for X6. So in this example, if you take a look, you'll find that, so remember the X3 you can originally solve for. You could check that separately. You can go through the details. X3 is available. You take Z3, which is the sum along the last column. You subtract Z8, normalize, which is this new shifted thing. And with appropriate juggling of the constants, you can get explicitly X6. You cannot, though, get, for example, X5. If you try to solve X5, you find you won't be able to get it because it's not uniquely solvable. But X6 is now uniquely solvable. And sure enough, there's a bonus because after all, X6 and X9 are so closely related that once you found X6, you've definitely got X9 as well. So in this case, we did get the bonus pixel. Now, that seems like a lot of goodies for free, right? We just increased the rank by 1, and suddenly we got new pixels, things happening, got a bigger field of view, a bigger region of interest. So what did we lose? It turns out we lost a little bit of noise properties of the region of interest reconstruction. So the noise in the region of interest reconstruction is slightly worse now than it was before. That's what we paid for to get that's how we paid to get a few more region of interest pixels. So so the way that works now is because when we increased the rank, we made another independent row of the matrix. It's the same size matrix. So one level of redundancy disappeared from the matrix, okay? So now we only have, in the new matrix C, we only have one row, which is redundant. Okay, so we lost some redundancy. Now, when you have redundancy in the matrix, what that does is it allows you to average out bad things in the data. So since we reduced redundancy, we expect to get reduced benefit of redundancy, in which, in other words, more noise in the new system where there's less redundancy. So here's a simulation study we did. So this X is the original image. I have no idea how Feriel picked off those numbers, but that's what our original image looks like. We did 10,000 realizations of the data corresponding to that, just using the matrix S and then separately using the matrix C. We added 1% noise to them. We performed image reconstruction. Well, any method of image reconstruction is going to accurately reconstruct the ROI. In our case, I think we used, I think it was a pseudo inverse, you know, in MATLAB or something. But I think anything would give the region of interest pixels accurately. And when I say accurately, of course, it's still a tiny amount of noise, but nothing compared to what will happen in the non-unique values. So here's the bias and variance of that, those 10,000 reconstructions. And if you look, of course, the top row is full of zeros. What that means is that the bias was zero. We accurately reconstructed the top row on average of 5.75, 7.43, 0.50. Always the reconstructions came out to average extremely close to that. So the bias was zero. And the other 6 elements, the second and third rows, were far away from the true values. Right? 9.88. So those are the absolute true values. So I'm not sure which way it went, but 9.88 might have been 5 point something in the reconstruction. So it was not even close. The top row on the right-hand side shows the variances. I've only put the variances for the 3 region of interest pixels because those are the only ones we care about. The other part of the image is crap. So we want to see what the variance looks like for the 3 region of interest pixels. Now we do the same thing again with the other matrix. Okay, so now what we expect is to see X6 and X9 also reconstructed well. And sure enough, it's true. So there's the top row, and there's the bias now in the right-hand column of the matrix is 0 as well. That's what we expected. And now those are the variances again for the region of interest pixels. And the important thing to see here is there's a slight increase in variance in the ones that were there before. Okay, so that's exactly what was predicted. So that's how we are paying for the new region of interest pixels. It depends. It's very hard to predict. It's complicated how to predict exactly how much variance change is going to be in each pixel. It depends a lot on the structure of the matrix. But overall, every pixel will get an increased variance or the same. There will never be a decreased variance from the new matrix. Let's do a medium scale example. I don't know how much time I have left. Very little, 9 seconds. I can do it. So here's something that almost looks like a Shep-Logan phantom, except it's still only 32 by 32 image. 396 measurements out of 1,024 unknowns. So it's definitely got a huge null space. The rank turns out to be 369. So that means there are 27 redundant rows in there someplace. Okay. And of course, the matrix size is 396 by 1024. So the other matrix C, we changed 3 of the values. And those values happen to be in columns 257, 272, and 513. The new rank did go up. So those were successful changes to the matrix. It went up by 3. So we expect to see 3 new pixels. So here's an image of the bias. So this time we're just putting an image of the bias. And as I probably forgot to mention, the region of interest, the existing region of interest was at 256 pixels in the upper left corner. So those are accurately reconstructed. That's the blue. And the red shows you that all the rest of that was reconstructed badly. This is a logarithmic scale, which is why you don't see any structure. Everything blue is 10 to the 12 orders of magnitude worse than everything red. So it's definitely a big difference. Now, what happens with the other matrix when we've changed those 3 values? So that's 3 values out of 400,000 values in the matrix, right? This is a pretty small change to the system matrix. And sure enough, pixel 257, 272, and 513 are now reconstructed accurately, just as we expected. And you look very closely, you'll find we had a bonus pixel. Next to pixel 513, I think you can see pixel 514 also made it in there. So in this case, we also got 1 bonus pixel. So now we try to plot the variance, which is done. We did the same calculation of the variances. So this 16 by 16 grayscale plot is the variance in the region of interest that was reconstructed. And I don't know how, it's not very big, but there's rows 8 is the middle row, row 12 is 3/4 of the way down, and row 16 is the bottom row. And the upper right plot is row 8. And the orange values that look like they're in front, the ones that are consistently higher than the blue values. The orange values are the result of the variance from the new matrix, slightly worse than the blue ones, and the same thing for row 12 and row 16. So again, the pattern of where the variance is increased and how badly is hard to predict, especially even more so in a big system. So that's it. The summary here is that if you increase the rank, you can get a bigger region of interest if you increase the rank, if you're lucky, if you do it right. Increasing the rank willy-nilly doesn't cut it. You really have to follow the theorem. If you change 2 elements of the matrix and you increase the rank by 1, you say, hey, great. You almost certainly won't get anything new. Okay? It really has to be just 1 element per one increase in the rank. And of course, as we just went over, the decreased redundancy causes an increase in the variance in the noise. So there are two papers that came out on the same topic. There's one just earlier on this year, which talked much more about the variance by Feriel, and there was a presentation by Michel de Vries at the 43D meeting last year, also on this topic, also in the same style. And my last comment is to thank my colleague Laurent Debat for his useful comments and helpful discussion last night when I was starting to prepare this. Thank you.
We have time for a quick question.
Thanks, Rolf. This is mind-boggling a little bit. So the change in the pixel value of the system matrix that increased the rank, that's actually shifting the line of measurement.
Right.
So you're changing your system design, right? Do you have guidance for how to choose that? Like, how do you figure out what pixel to change in the system matrix?
Well, you really have, so what you're asking is how do you change your physical system, your detector system? What you like to do is just move the detector a tiny amount and get all this magic out of it. So yeah, what I didn't mention is up in that previous image, there were actually 3 lines that showed which lines in this larger example. You probably can't see them. There's 3 blue lines and they're all very peripheral. They're actually outside the chaperone, they're on the boundary. And if you shift an element, can you see them? There's one at the top and those 2 at the sides. If you shift that slightly, then all the pixels serve the same contribution except the end one when it goes out. So that's one place. That's how we did these experiments. Other than that, it would be hard to do. It would be hard to change the contribution of a pixel in the middle without changing the contribution of other nearby pixels. So the edge pixels are the easy way to do that, or the easiest way to do that.
I'm sorry, we're running behind time. We need to move to next speaker. So could
I'll talk to you later, Shashwan.
Sorry about that.